Safe execution isn't a prompt, it's an isolation boundary. Sandbox tool code, so one bad run can't hurt your system. This is the setup you'll be able to run after this, which isolates untrusted code with tight limits and then runs it to capture a safe result. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Untrusted tool-generated code shows up in many pipelines. A model suggests a helper program, or a tool returns a snippet to run. That code can be buggy, leak data, or consume all your CPU. Hard sandboxing treats this as an operational problem. Success means you can execute outputs and still guarantee no exfiltration, no system corruption, and bounded cost. Think containers as a safety box you control. They let you cap memory, CPU, processes, network, and file system access. The idea is simple. Give the runtime only what it needs, measure what it does, and tear it down. That trade-off gives pragmatic security without cryptography or exotic hardware. We will build a small, repeatable flow. First, we check the runtime is reachable. Then, we run a tiny expression inside a locked container. Then we add a timeout watchdog. Next, we expose a read-only workspace so tools can see inputs but not overwrite them. Finally, we run a production-style baseline that applies all the limits together. Now, we'll run a quick runtime check. This snippet verifies a working Docker engine connection using the Docker SDK for Python. The function Docker from env creates the client DC by reading the local environment, so it targets your local daemon without extra config. The variable OK captures dc.ping, which is a lightweight health check that returns true on success. The string img sets a clear base image choice we will reuse for all sandboxes, keeping decisions deterministic and fast. If you change img to a larger base, polls get slower and memory usage rises. The printed result confirms Docker is reachable and records the chosen image for later steps. Next, we'll execute a confined task inside the runtime. This example executes a tiny Python expression inside a heavily restricted Docker container using dc.containers.run. The variable cmd holds the in-container command, while memlimit and nano-CPUs cap memory and CPU to bound cost and latency impact. The settings pins limit and user drop process count and privileges, and network disabled cuts egress entirely. Setting read-only seals the root file system, while tmpfs provides a small writable scratch area at tmp without persisting data. The container runs detached. c.wait synchronizes, and c.logs reads the output for inspection. Increasing memlinit or nano-CPUs speeds heavy tasks but weakens guardrails. The printed status and output confirm the sandbox executed safely. Next, we'll add a timeout and external watchdog. This code adds a wall clock timeout using the Docker SDK, which is essential for runaway tool calls. The variable cmd sleeps for 5 seconds in the container, and we run it detached to control it externally. After time.sleep for 1 second, c.reload refreshes the container state, and we compute alive from c.status to see if it is still running. If it is, ckill sends a sigkill to terminate it. Then cwait ensures the exit is recorded. Reducing the sleep gives tasks more room to finish. Raising it tightens latency protection. The printed values show we hit the timeout and force-stopped the workload. Now we'll expose a minimal host workspace safely. This snippet prepares a tiny host workspace and exposes it read-only to the container. The variable WRK is a new temporary directory, and we create a txt with a short payload to simulate tool inputs. The call dc.containers.run maps WRK to /data using volumes with mode set to RO, ensuring the container can read but cannot modify or exfiltrate host content. The command prints the file's content for verification, and we decode logs to compute read-len deterministically. If you switch mode to RW, writes would succeed, but risk tampering. The printed length and mount path confirm that reading works while preserving host integrity. Finally, we'll put the limits together into a baseline run. This example assembles a production-ready baseline using the Docker SDK to run untrusted code safely. The variable cmd lists files under data, so the container proves access only to the read-only mount. The call dc.containers.run applies memlimit and nano-CPUs to cap resources, PIDs limit to restrain forks, and user to drop privileges. The flags, network disabled and read-only, cut egress and write access, while tmpfs provides ephemeral scratch space. Volumes binds WRK into data in read-only mode. We wait for completion, measure log size for monitoring, and remove the container. The printed status and byte count confirm a controlled, observable execution. In a real project, this pattern maps cleanly. Use the check to gate CI runners. Use the tiny runs to validate tool outputs before escalating to larger clusters. The read-only mounts let models inspect datasets without risk. The watchdog protects latency-sensitive services. Recap: hard sandboxing is running untrusted code inside a tightly constrained container. Use it when you must execute model or tool-generated code but cannot trust its behavior. Caveat: containers reduce risk but do not eliminate it. Combined with policy, auditing, and minimal input sharing. Next step: tune memlimit and nano CPUs for your actual workloads, while adding timing and output checks to balance safety and performance. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.